Things up today with our review of time-varying fields and plane waves, which are the solution to Maxwell's equations. This is going to be very fast, very brief, and really hit the high points and some of the big ideas behind this. If you want to explore more, you'll need to go back and watch the other videos. So the first thing we started off with was this big idea of displacement current. And essentially what we did is we thought about a very simple circuit. Essentially we have some kind of battery here, a switch we're going to close at time t equals 0, and it's going to charge up a big capacitor with some capacitance C, and essentially we put a current meter that's going to measure the current. And so let's see what happens when we close the switch. The current jumps, it's negative here, it's positive here, and over time as the capacitor charges, essentially the current drops to 0. Let's watch that one more time where we open the switch, close the switch, watch the current jump high, and then slowly drop down to 0 as the capacitor charges. Now this is kind of confusing because if we have a capacitor, there's some kind of big insulating gap between those plates. That's what makes it a capacitor. And we learned that essentially what happens is because you're going to get an electric field set up in this direction, the changing electric field is similar to a current. We call it a displacement current. So the overall current isn't just the conduction of electricity. It has to do with the time change of the electric flux between the capacitor plates. And so we've defined both a conduction current and a displacement current. So a time-changing electric flux acts like a current. The next big idea was that we saw we got rid of a lot of the whole barn of equations we had when we had static fields or time invariant fields, and that when the electric and magnetic fields varied with times, we could essentially describe these with four basic equations. And these equations are known as Maxwell's equations, and they have two forms. There aren't 8 equations, there are only 4 equations. There's a differential form involving derivatives that you use when you know fields over a region of space because derivatives aren't defined at a point. And there are integral forms of the equations that are more useful when you essentially have discrete items, things like wires and plates with sharp edges, the types of homework problems you typically get. The differential forms are essentially Gauss's law, the fact that you don't have magnetic monopoles or magnetic charges, the fact that the curl of the electric field essentially is related to the time change of the magnetic flux. This is Faraday's law, and then Ampere's law, where now we write essentially the curl of the magnetic field is equal to the current, which includes both the conduction current and the displacement current we just learned about. The integral forms of these are exactly the same thing. Gauss's law expressed as integrals, no magnetic monopoles, Faraday's law expressed in integral form, and again, Ampere's law with both of our definitions of current. It's important that even though Maxwell's equations, especially in their differential form, are pretty short and look pretty simple, when you expand these things out in full Cartesian coordinates, you see things necessarily aren't trivial. For example, here's Faraday's law in the differential form, one of Maxwell's equations. We see if we expand this out, recognizing that the electric fields now have 3 spatial dimensions and 1 time dimensions, that this very innocuous looking equation gets to be ginormous. One neat thing about this ginormous equation is we can write it in terms of 3 orthogonal components, an x component, a y component, and a z component, and because in a good coordinate system the x, the y, and the z axes are orthogonal to one another, we can solve 3 separate equations and deal with things a little bit more easily that way. Another one of the big ideas we talked about is that time-varying fields are going to create new time-varying fields. And so in order to illustrate this, essentially what we did was we considered another very simple circuit where we have a battery, a switch we're going to close at time t equals 0, and a big giant plate. And essentially what we're going to do is when we close the switch, we're going to see some current I, given as the light blue lines, flow in that direction. And we're going to make the assumption that I is very uniform inside the plate, and we're going to look at the plate and the surrounding region both from the top, or in that direction, and this is the top view, so we're looking down, and from the side view, or this direction. And this is what the side view is going to look like. And I'll have top view and side view on these so we know which is which. In both our top view and side view, we can think about what the current would be. It's essentially going down into the screen in the top view, as shown by those blue vector symbols. In the side view, the current's just flowing down uniformly through the plate as looked on from the side edge. So here's the side view right here. Here's the top view. This is our overall circuit once we've closed the switch, and we're looking immediately after that current starts to flow. We're going to represent magnetic fields in terms of green arrows and green vector symbols, and electric fields in terms of blue arrows and blue vector symbols. Now there's an inherent assumption we're going to make here, which is that the fields don't establish themselves instantaneously. They take a little while to propagate. So let's start with a very qualitative look at what Maxwell's equations tell us about the types of fields we can expect. And we're going to start looking at our side view first using the integral forms of Maxwell's equations. So what do we think is going to happen? When we turn this current on, we know we're going to create a magnetic field, because Ampere's law tells us that the magnetic field surrounds essentially anything that carries current. And so from the side view, if I use the right-hand rule and my current's flowing down, I can see that on the left side, the magnetic field is going to be flowing into the screen, as indicated by those arrows. On the right side, it's going to be pointing out of the screen, as indicated by those vector symbols. And we know that once this is established, at the first moment in time, that magnetic field is going to be really close to the plate that carries current. But essentially what's going to happen is this magnetic field is going to propagate outward. Let's watch that again. There's going to be some velocity, and that magnetic field is going to propagate outward with time. Well, now I can use Maxwell's integral equation. Essentially what I'm going to do is I'm going to draw a surface, ds, right here in the plane of the screen, and I know that the rate of change of the magnetic flux that goes through this surface right here is equal to the line integral of the electric field that goes around that. And so obviously I have a magnetic field. The line integral is going to be done around this box right here, and the magnetic field is going to be moving out in that direction. So what's going to happen with this? Essentially, what you can think about is that because the magnetic field is moving out in that direction, the flux is increasing with time, and so you're going to essentially get a positive value of that flux, because more flux is going through that surface, the magnetic field propagates outward. That says it's going to in turn create an electric field. What direction does that electric field go in? Well, all we have to do is sum up the sides of the boxes. We know that there's going to be zero magnetic field on that side of the box right there, because nothing's reached that. We know because we're going around a line, and because of symmetry, that side of the box and that side of the box are going to cancel out, and essentially all the electric field is going to be around that side of the box. So through some simple geometry arguments, we essentially can relate the electric field to the magnetic field, the velocity it's moving, and the length of the box, L. And we did this before when we were deriving the video previously. So what we see essentially is that the velocity of the magnetic field, since it's going outward in time and changing in time, creates an electric field. So we can essentially write the electric field going up in that direction. So the time-changing magnetic field creates that electric field. We can get exactly the same thing by using the differential form of Maxwell's equations, as one might expect. But in this way, we're saying the curl of the electric field is equal to the current, both the conduction current and the displacement current. Well, it turns out that since we're in free space, sigma is equal to 0, so that term drops out, and all we have to consider is the displacement current. So let's see how this works. Essentially, we know that the magnetic field is going to get weaker and weaker as we move further and further away from that plate, because that's what Ampere's law tells us. And so essentially, if I think about the curl of this field the way I've drawn it, I can figure out what direction the time rate of change of the electric field is going to be in by putting in a paddle wheel and figuring out which way the paddle wheel spins. Well, it's pretty obvious that that paddle wheel, although you can't see it very well here, is going to basically spin in the counterclockwise direction, because this side gets a stronger force than this side over here. I can do the same on the other side, essentially, and my paddle wheel is going to spin in the opposite direction. For both of these, if I use the right-hand rule, I can draw the electric field rather straightforwardly, and I see it's going to be pointing right out of the screen at you. So in both the cases, whether we use the integral form or the differential form of Maxwell's equations, we see that the change in the magnetic field creates an electric field. So what we've seen is that we initially had a current flowing down in the side view and down into the screen in our top view. We saw in the last slide that this essentially created a magnetic field, shown as the green lines, and the magnetic field in turn created an electric field. Well, what does that electric field do? Let's start again with our integral form of Maxwell's equations. Essentially, we have Ampere's law, and we can neglect the conduction current component because, again, there's no conduction in free space here. And so we know the line integral of the magnetic field is equal to the time rate of change of the electric flux. Well, I can do exactly the same thing I did before and think about drawing a plane and calculating the electric flux that moves through this plane right here. We know the electric field has some velocity outward, so the flux is going to be increasing in this with time, so that term is non-zero. And just like before, I can sum up the sides of the box and say there's no magnetic field there. This side and this side are going to cancel out, and so all my magnetic field is going to be on that side of the box. When I go ahead and plug that in, I get this term right here. And so essentially what we're going to see is that the electric field in turn creates a new magnetic field pointing in that direction and that direction when I work everything out. It also turns out that if I substitute in the relation between the electric field and magnetic field I derived in the previous slide, and we saw this before, that we can actually calculate the velocity that depends on both the permeability and the permittivity. More on this later. Let's use the differential form of Maxwell's equations to take a look at this. Essentially, here we know that the curl, or the spatial curl of the electric field, is equal to the time rate of change of the magnetic flux. Again, what we'll do is we'll put our paddle wheel, and although the animation isn't going to work very well, we essentially see that our paddle wheel is going to spin in that direction because it gets a stronger force on the side closer to the plate because the fields drop off in strength the further away we move. Similarly, on the other side, we can put in another paddle wheel and see it moves in the opposite direction. So what have we learned? We've essentially learned that using either the integral form or the differential form of Maxwell's equations, that the initial magnetic field gave rise to an electric field, which gave rise to a magnetic field. And so time-varying fields create new time-varying fields. Magnetic to electric to magnetic to electric. So let's take a look at this and summarize all of what we've learned about this very qualitative. Either on our side view or on our top view, if we sort of extend this logic out, which is very sort of hand-waving, very qualitative, it's not what you would do for the answer to a test or anything, we can essentially see that we get fields and the directions of the fields shift out of the screen, up along the screen, into the screen, down the screen, out of the screen, and so forth, for either the side or the top view. So it really should not surprise us that a solution to Maxwell's equations is a wave, because essentially you'd have a peak of the wave here, a negative going part of the wave here, a second peak of the wave there, and the wave, as we saw, is going to propagate with some velocity, and that velocity depends on the material the wave's propagating in, which is again determined by the permeability and the permittivity of the material. So that was my hand-waving explanation of how we actually get waves from Maxwell's equations and how Maxwell's equations in a very qualitative way predict waves. Of course, there are probably a lot of famous physicists, including Maxwell himself, who are rolling over in their graves on the sort of sloppy explanation I've done. So let's take a look at a more mathematical explanation. We can essentially use a vector calculus identity given right there, and basically if we assume the permittivity doesn't vary in space, in other words materials are isotropic, we can pull epsilon out and we can essentially rewrite that equation in this form right here. We make another approximation that there's no free or movable charge. In this case we can use Gauss's law and basically set del dot D is equal to 0. That's going to cross that term out of the equation right. This simplifies the equation to this format. Next, what we're going to do is we're going to substitute in another one of Maxwell's equations, and for this del cross E, we're going to substitute negative dB dt, and thus we turn the equation to that form right there. If we make another assumption that the permeability doesn't vary in space, again, the material is isotropic, that allows us to basically pull mu away from B and pull it out of the parentheses, and so we can rewrite that last equation in this form right here. Again, we make another substitution using one of Maxwell's equations for del cross H, essentially writing it as the current, both the conduction current and the displacement current, and we substitute that into this equation right here. And this allows us to rearrange the form to something that looks like this, which in turn goes to what's known as the wave equation. And this is a partial differential equation with both spatial terms and time terms that relates to the electric field. It turns out it's a very famous equation whose solution is a wave. So essentially we assume a time variation of the electric field that has a sinusoidal form, and the solution, or one of the solutions of this equation, is given by what's in the yellow box here. It's essentially a wave that varies in 3 dimensions of space, x, y, and z. It varies in time. It has a vector amplitude, which means the electric field has an amplitude but also points in a particular direction, and it has a phase that varies sinusoidally with both time and with space, where the term k is given by that term right there, and of course omega is just 2 pi times the frequency. Well, after taking you on that little mathematical derivation, let's go back to some of our big ideas. It turns out that this solution right here is called a plane wave, and plane waves are possible solutions to Maxwell's equations. They're not the only solution, but they're actually about the most useful solution to Maxwell's equations there are. And essentially we're assuming the plane wave moves in a direction given by the wave vector k. So k is the direction it's propagating in. R is the point we want to measure the electric field at. And we're assuming this plane wave is infinite in extent in the x and y directions, assuming it's moving in the z direction, or it's essentially infinite in extent orthogonal to the k vector. So let's take a look and see what this plane wave looks like. Let's pick this point on the plane wave, where we're right at a peak of the plane wave. Essentially what that means is in the plane orthogonal to the direction the wave's traveling, or orthogonal to k, the electric field is going to have a constant value. It's going to create a vector field and map a vector to every point in space. But every single one of those vectors are going to be pointing in the same direction at some given point in time. If we pick another point on the wave, let's say this point down here near a trough of the wave, again, the electric field is a constant value, but because the field's negative, the vectors point in the opposite direction. And so now we see how the wave begins to vary with space, that sometimes the electric field vectors point one way, sometimes they point another way. If we take a third point on the wave, essentially, where the value of the wave is 0, again, everywhere in space and time we get the exact same value, but there's no electric field vector at this particular point in space. A third point in space, or a fourth point I should say, at some value that's positive but not at the peak, will essentially have electric field vectors pointing in the same direction, but they won't be quite as long because the amplitude's not at its peak. And so we're starting to get an idea of this plane wave variation in space as mapping electric field vectors that point along the same direction, but they can point in one way or in the opposite direction depending on whether this phase term k dot r is positive or negative. And oftentimes we simplify this wave equation by using the fact we can rotate our coordinate axes in any direction and essentially say k is along the z direction, in which case we can get rid of the vector component and write the plane wave with just a k dot z or a kz variation, which makes things a lot easier since you don't have to deal in 3-dimensional space. And this is what we'll be talking about for the rest of this video and the approximation we used in a lot of the previous videos. So a quick summary of plane waves, what we've learned so far. They're a solution to Maxwell's equations. If you simplify them so the wave's moving along the z direction, you have this phase term which varies in time and space. The term k is 2 pi over the wavelength, where the wavelength is the spatial distance between two peaks of the wave. Let's put lambda right there. Omega is the frequency, and the relationship between omega and the wavelength and the velocity, v phi, the phase of velocity, is given by this term right here. Omega over k gives you the phase velocity. We can see that because omega is just the spatial, or excuse me, the temporal rate of change of the phase. K is just the spatial rate of change of the phase. And of course, if we solve this out, these delta phis are going to cancel, and omega over k gives you the phase velocity, or how fast the wave is traveling, which we know is equal to 1 over the square root of mu epsilon. In most dielectrics, the permeability, mu, is just equal to the permeability of free space, and so we can write our phase velocity as c over the square root of the relative permittivity, or just C, the speed of light divided by the index of refraction, where the index of refraction is a term that's given by the square root of the relative permittivity of the wave. You can see I'm struggling here a little bit to try to get this idea of a plane wave across to you, and the reason that I'm struggling is that it turns out that in fact that plane waves are really hard to draw well. And the reason for this is that they change both in time, because we've got this time-dependent phase term here, as well as in space, because we have the spatially dependent phase term, where here I'm assuming the wave's moving in the z direction. So what I've done is I've gone ahead and gone out to the Falstad 3D wave box and created a plane wave in it using the Java applet. And essentially what we're going to say is that the z-axis is along this direction. We're going to watch a plane wave move in the z-axis when I start this video, and I'll pause it occasionally. So you can see essentially that the plane wave is moving along the z-axis. The green are the positive areas and the red are the negative areas where the field is in opposite directions. Now what I've done here, let me stop this, is I've gone ahead and asked the applet to give me a slice, essentially along, if we think this direction is the z-plane, and let's go ahead and call this direction the x-plane. We're looking at the xz plane. And you can see that essentially what's happening is that we can see the lines of phase, where we have essentially positive phase here, negative phase here. Let's let it run a little bit, and you can see that those phase things move in time. Now let's take essentially a slice in the YZ plane, and we see exactly the same thing happening, that in both planes that contain Z components, we see the axis. But look what happens when I take the XY plane. This is the plane where the field's constant in, and I see one value throughout the entire plane. And again, in 3 dimensions, this is what the plane wave looks like. One of the other big ideas here is that plane waves are very useful when you're far away from a source. And the thinking is that if you're up close to where the radiation's emitted from, so we're getting sort of circular waves of radiation emanating or propagating out in that direction. Think of dropping a rock in a pond at this place right here. That the wavefronts are obviously curved when you're close to where you drop the rock. But as you move away, these curvatures get bigger and bigger, and essentially in a small area they act pretty much like a plane. So when you're far away from a source of electromagnetic radiation, a plane wave is what you're going to see. It also turns out that, as we'll see later, superposition holds for plane waves. So if you understand Fourier theory, you can build up more complicated things once you have the plane wave solution if necessary, just like you can build up any signal from a bunch of individual sine waves. Now this idea of superposition is important actually, because what we have is, let's say we've got an electric field that's polarized along a direction that's not in x or not in y, and our wave's propagating here in the z direction. It turns out that we can sum up this wave by thinking about adding an x component, which I'm going to show as a red arrow in the slides that follow, and a y component, which is shown as the blue arrow. And essentially, as you can see, the sum of the x component and the y components of the electric field are going to give me an electric field that goes in this direction. I'm drawing a double arrow green line because we know the electric field is going to oscillate in time. And so what we're saying here is that since superposition holds for electric and magnetic fields, and plane waves are just composed of electric and magnetic fields, that superposition holds, and if I have some wave pointing in an arbitrary direction, it is equal to 2 waves that are added up that essentially point in the same direction. So I can represent it either as a single wave or as the sum of 2 waves. And that's the really important thing about superposition, is you can sum up any number of waves to give you a single wave. Now that we're talking about the direction of the electric field, this leads us to the next big idea, which is the idea of polarization. And we use polarization in this case to basically indicate it's the direction the electric field points. And different waves can have different polarization states, but essentially all that means is they describe how the electric field vector is going to point. So here we have the electric field in the y direction. The direction of polarization is y. We say this is a y-polarized electric field because that's the direction E is, either along positive y at some points in time or negative y at other points in time. And we can also talk about planes of polarization, because this wave's propagating in the z direction. We talk about it being E-plane polarized in the YZ plane. We talk about the magnetic field plane as the H-plane. And essentially what we do is we distinguish three different ways a wave can be polarized. The first of these is what we call linear polarization. And linear polarization really just means that the electric field only points in one direction, no matter where you are in space or where you are in time. And so let's take a look at this. So essentially what we have here is the first case is we have a wave that's polarized along one of our axes. E is in the x direction. We would essentially just write the electric field as a function of space, x, y, and z, and time in this term, that we have some amplitude Ex with a phase term, and this whole term is pointing in the x direction, and we've got nothing in the y direction. So this is the simplest case of linear polarization, or polarization along the x-axis. Another way we can have linear polarization is to have two components. Here we have an x pointing component given in red and a y pointing component given in blue. The overall electric field essentially points in one direction. It points up this way, but we know it's going to oscillate in time. But it's essentially going to point along one axis, and that's what linearly polarized is. The electric field is a function of space. X, y, z, and time is essentially the x component with its phase term plus the y amplitude with its phase term. But notice both these phase terms are exactly the same. Both of these waves oscillate together. And this video will basically show the two components oscillating together. Essentially what we have is the x component given by the red line, the y component given as the blue line. The overall field is going to be the green line, and we're essentially, when I start this video, going to see the wave oscillate linearly. This is a case of linear polarization where both the x and the y components are oscillating in phase, red x, blue y, as you can see, and you'll see that although the wave's at an angle, the polarization is linear. It still just makes a line as it propagates through space. Another case of polarization is what we call circular polarization, and this is just another name. Here we have two equal components that have a 90-degree phase shift between them. There's some phase difference delta theta that's either plus or minus 90 degrees. So how does this work? Essentially, we have some x component of the field, and we add it, we just sum, that's superposition with a y component, and the overall field is essentially going to be the x component plus the y component, so we might expect it to be linearly polarized at 45 degrees. But notice we do something different here. We take and add basically a 90-degree or pi over 2 phase shift to one of these components. And you'll notice for circularly polarized radiation, we need to have the amplitudes of the two components, the x component and the y component, be the same, and we've represented this by E naught in both of these cases. And of course, what happens if instead of a plus 90-degree phase shift, we get a minus 90-degree phase shift, we essentially just have the y field going in the other direction, and we're going to change the direction of the electric field and actually the direction it rotates, but we still have circular polarization. So let's stop and take a look at a little video and see how that works. Here's the video, and what you're going to see is the y component in blue and the x component in red are going to oscillate 90 degrees out of phase, and you're going to see this wave trace out the corkscrew pattern you see in time. This is what happens when we have two components that are 90 degrees out of phase. The x component is red, the y component is blue. It's called circular polarization because the overall green field vector, as you can see, makes a circle, and the wave itself sort of corkscrews as it propagates through space along the z-axis. The final case we want to talk about is something called elliptical polarization. And this happens when you have unequal components, that you have an x component and you add it with a y component, but the x component in this case is longer than the y component. They have unequal lengths. Essentially, you get the same type of thing we had before, but we have different amplitudes for the x and y component, and we have a phase shift theta that's not equal to 90 degrees. And essentially what this is going to do is it's going to trace out an elliptical shape, and thus we call it elliptical polarization. So let's stop and take a look at the video here. The last case is elliptical polarization, where we have unequal x and y components, and the phase difference is not 0 degrees. It's called elliptical polarization because the overall vector traces out an ellipse, and you see there's sort of a skewed corkscrew as the wave moves through space. We just saw that the direction of the electric field is determined by something called the polarization, and the electric field can change in space and time and direction depending on whether it's linearly, circularly, or elliptically polarized. The next set of our big ideas has to do with the waves propagating through material. So if the wave propagates through a material that has some conduction or has a property called loss, the wave gets attenuated. So how does this work? Well, essentially what we do is we define a complex permittivity given by the permittivity of the material as well as the conductivity sigma divided by omega. And if we assume the material is non-conductive, this goes away and we don't get any loss. However, we do have some conductivity. We see the permittivity has a real part and an imaginary part. Essentially, we can then write our K vector as having two components, an alpha and a J beta component. So we can rewrite the electric field of the plane wave as having a vectorial amplitude times a term that's attenuation, where the amplitude decreases the further it travels, and the usual phase term, where in this case we've replaced K previously with beta. It turns out that the alpha and beta terms can be calculated from the real and imaginary parts of the complex conductivity. The expressions are complicated, but a computer or calculator lets you do this fairly straightforwardly. So let's look at what solutions of this plane wave might look like. If alpha is small, essentially you get the wave that's shown right here. You essentially get a decay, but it has low absorption and the amplitude doesn't decay much as you propagate. However, as the absorption goes up, you get a medium absorption. You see a faster decay of the amplitude. And as alpha gets bigger and bigger, you see a larger and larger decay. And essentially what you're going to see is that you get this exponential dependence of the amplitude the further and further you go along Z into the medium. We talked about another big idea, that the fact that in highly conductive materials the attenuation is very, very fast. It actually increases the resistance of wires and conductors at high frequencies. And the reason for this is that rather than conducting over the entire surface area as shown previously, essentially the wave doesn't penetrate very far into the conductor. Essentially it only penetrates a distance about 1 over alpha. And if we go ahead and rederive our expression for the resistance of a wire, we find something that looks like this expression right here, where now it is both conductivity dependent as well as absorption coefficient dependent, and that absorption coefficient essentially depends on the frequency. We also in the previous videos ran some examples to show the behavior. So let's look at our general plane wave, essentially, given by this expression right here, the vectorial amplitude, an attenuation term, and a phase term. And when I run this video, we're essentially going to see a plane wave coming in at some phase velocity into an interface with a medium. Out here, beta is equal to 1 and alpha is equal to 0. The medium itself has beta equal to 3 and alpha equal to 3. So let's run this and see what it looks like. Essentially here you see it coming in. The wave slows down and has a lower phase velocity. We get into the material. Notice that the peaks, or the wavelengths, get smaller. The peaks get closer together spatially because of the slowing down of the wave. Let's watch that again and see how that works. And you see the attenuation, the amplitude gets smaller and smaller as you go into the medium. It's worth mentioning that this is a highly simplified nonlinear case where I'm showing how alpha and beta affect a wave, but it really ignores the more complex relationships between alpha and beta. Another one of the big ideas is that when waves intersect a medium, they don't just go right in. You actually get some reflection and transmission into this medium. And essentially, let's first talk about the direction the wave goes. So we have some incident wave coming in at an angle k sub I here, or coming in a direction k sub I given by the k vector, and essentially we define the incident angle as the angle relative to the surface normal, because remember we can only define surfaces by their normal. And so we're going to call that incident angle theta sub I. The direction the wave propagates are given by two laws, the law of reflection and Snell's law. The law of reflection simply says that the reflected angle theta sub r, that's that angle right there, is equal to theta sub I. Snell's law relates basically the incident angle theta sub I to the angle the wave's transmitted, theta sub t. And essentially what we see here is that this relationship involving the signs of the angles and the index of refraction of the medium on the incident side and the transmitted side is going to determine that transmitted angle. The index of refraction, as we learned previously, is essentially given by the square root of epsilon and of mu if mu is a magnetic material. And if it's complex, you write it in this form. And generally we use indices of refraction to characterize materials. It turns out that it's not only the direction of the waves that change. So this incident wave comes in and changes direction and comes out as a reflected wave, and it also goes to a transmitted wave. But as you might imagine, because some of the incident energy gets reflected and some gets transmitted, the amplitudes of these reflected and transmitted waves need to be calculated as well. And they change, and they're determined by something called Fresnel's equations. The next of our big ideas is that while the law of reflection and Snell's law determine the direction, Fresnel's equations determine the amplitude, and so these laws completely determine the reflected and transmitted plane waves. Snell's law essentially relates the reflected electric field to the incident electric field by a reflection coefficient that we're going to call R, and it turns out that the direction the electric field is in makes a really big difference in the amount that's reflected or transmitted. We talk about S, or perpendicular polarization, by defining a plane of incidence, and the plane of incidence is the plane that contains both the k vector and the surface normal, so that's the gray plane right here. And if E sticks up and down out of that plane, then we call it S, or perpendicular polarized, because E is perpendicular to the plane of incidence. And these are Fresnel's equations right here that give the reflection coefficient, or the fraction of the incident wave that's going to get reflected, as well as the transmission coefficient, or the fraction of the incident wave that's going to get transmitted. We have similar equations, but slightly different for what we call p-piercing or parallel polarization, and this is the case where the electric field vector lies in the plane of incidence rather than sticking up and down from it. And as you can see, we've got different sets of Fresnel's equations that look very similar, but they also calculate the reflected and transmitted electric fields. It turns out that Fresnel's equation gives us two special cases. In the first, all the electric field is reflected, and in the second special case, all the electric field is transmitted. The first case, where all the field is reflected, comes when you're going from a material where N sub I is greater than N sub T. You're coming from a more dense medium into a less dense medium. In this case, if the incident electric field coming in at angle theta I from the surface normal is greater than the arc sine of the transmitted index divided by the incident index, then all the radiation gets reflected and the transmitted field is zero. And so for big enough theta I, you get total internal reflection going from more dense media with large indices to less dense media with smaller indices of refraction. The second case is called Brewster's angle, and this only occurs for p-polarized radiation or parallel polarized radiation, but at a particular angle of incidence, theta I, given by this equation right here, where theta B is known as Brewster's angle, the reflection goes to zero and all of the incident radiation is going to get transmitted into the material. Another big idea and why plane waves are useful is they can carry energy from space to space, even though there's no medium except vacuum for the waves to go through. In other words, you can carry energy through space and you don't need wires. This is, in essence, how solar energy works. Essentially, the way we calculate the amount of energy carried by a plane wave is we think about the wave having both electric and magnetic field components, and if we take the cross product of the electric and the magnetic field, we get a second vector called S, the pointing vector, and essentially the pointing vector gives us the joules per unit area per time, or in other words, the watts or power per unit area. It turns out that if you really want to calculate the average power, which is a more useful thing to do, you have to basically integrate the pointing vector over one cycle of the wave, and essentially you come up with an equation that looks like this. And so essentially you can relate the intensity, the power per unit area, to the strength of the electric field using this equation right here, and the result of this is that plane waves carry a given amount of energy per area per time that depends on the strengths of the electric and magnetic fields. Of course, if you have a plane wave moving along hitting a surface that's at an angle, you have to calculate the flux by basically taking the dot product of the pointing vector with the surface normal and the area of the surface you're hitting, and we've talked about that in the previous videos. Beyond carrying energy, plane waves can also carry information. And to understand this, we have to understand the Heisenberg uncertainty principle, which essentially states there's a limit to the accuracy of any measurement. And there are lots of ways to state this, but the two ways we're going to explore are that the variation of the y component of the k vector with how accurately you know the position of the wave in the y direction has to be greater than or equal to 1/2, or the bandwidth of the signal, delta omega, times the how accurately know the position of the signal in time also has to be greater than 1/2. So how does this work? Well, this is pretty simple, and so let's look at this second case right here. How accurately you know the radial frequency and how accurately you know the time have to be greater than 1/2. How does this work? Essentially, let's take a wave, and if we assume the wave is infinite, and I want to calculate the frequency, what I'm going to do is I'm going to pick this point on the wave and this point on the wave, count the number of cycles in between, and because I've got a long measurement in time, that measurement's going to be pretty accurate. But if I cut my time window down, now essentially what I'm having to do is measure that point and that point. My measurement gets a little bit less accurate. Here we only really have 3 or 4 cycles we can measure over. My measurement becomes less accurate. I know my frequency less accurately because my time window is shorter. Similarly, if I only have 1 cycle of the wave I can measure, I have a smaller time window. I don't know my frequency quite as accurately. And the real kicker is if I only measure a very, very small slice of my wave, it becomes very difficult to accurately determine the frequency of what this wave might be. And that's what this says. If you have a big time window, you know the frequency pretty accurately. If you have a tiny time window, it's really hard to know exactly what the frequency is. God damn it. Let's take a look at the other case, looking at the propagation of wave. And the way we're going to consider this is we're going to have some wave propagating in the YZ plane. And essentially we know we can write our k vector as the x component, which we're going to ignore here, plus the y component, plus the z component. So for this wave propagating in an angle we'll call theta right there, mostly it's z component. There's a very small y component pointing up in that direction to the vector, but most of it is the z component pointing along that way. And we know the ratio between the y component of the vector and the z component of the vector is equal to the tangent of that angle right there. The case of our plane, God damn it. The case of our plane wave is one that comes from an infinite source because the plane wave is infinite in extent and it only goes in one direction. So in this case, k only points along the z direction. In other words, ky is equal to 0 because delta y, the size of the plane wave, is infinite. And that's essentially what the Heisenberg uncertainty principle says. However, if I go ahead and look at a point source, the opposite extreme, where the size of my source is equal to 0, delta y is equal to 0, notice that ky is equal to infinity. I have waves going out in all directions, spherical waves from this point source, so there really is a very large spread of ky values. Ky is 0 here, larger here, still more ky, and less kz, more ky, still more ky. In other words, if I were to calculate the tangent of the angle of a spherical source, you're going to find the tangent of 90 degrees goes to infinity, or delta ky is equal to infinity. Of course, we can think of cases in between this, of a source that's not a point source, that has 0 spatial dimension in the y direction, or infinite extent in the y direction. In other words, a finite source. In this case, we know there's some variation to ky because the size of the source delta y and delta ky are greater than half. And the way you would think about this is that you have waves going in that direction and also that direction that get emitted from a finite source. What Heisenberg uncertainty principle tells you is that the smaller you make a source of radiation, the less and less plane wave-like the radiation coming from that source is. You have to have a very, very large source for your radiation to create a true plane wave. The same idea holds with the Heisenberg uncertainty principle that related the size of the source to the accuracy with which you know the direction the wave's propagating to the extent of the wave in time and the amount of information you can send. So if we take a wave, and this is really our plane wave solution here, that is infinite in time, because in our standard plane wave solution, time goes on forever. We get one single frequency that just goes and goes. The time window of this wave is infinite. It goes from the beginning of time to the end of time. and it has one frequency. There's no variation whatsoever in the frequencies. The opposite case is what you know in electrical engineering is the Dirac delta function. We know the time of this Dirac delta function goes to 0. In this case, it takes a very, very narrow slice of time. Delta t goes to 0, but we know the spectrum of the Dirac delta function contains all frequencies. So how do we send bits of information, which a Dirac delta function is, on a wave which we know to be infinite extent and essentially can't carry anything at all except the frequency of the wave? Well, we look at the middle case again. We have a wave that's compressed in time, so we send a self-propagating pulse of information, and again, the frequency spread and the number of frequencies we need depends on the time width of this pulse given by the Heisenberg uncertainty principles. Hopefully this has been a good wrap-up of all the things we've covered in the previous talks in a relatively condensed form.